2.5 chain rule. In one of the examples I gave it to you in 2.3, right, taking derivative of functions which has a formula x plus 1 quantity square. We don't have a formula to take the derivatives of the composition functions back then. So therefore, what we did is we rewrite it into a product rule and a product format, and take the derivative using the product rule. But however, there are many functions that you cannot break it down like that. For example, if I say like square root of x squared plus 1, that is also a composition function. Right? We cannot break it down 1/2 power into in terms of product. So in that kind of situations, it is unnecessary that we need to learn the methods of taking differentiations of uh, you know the composition function in this section. So the the chain rule basically say that first you need to uh, be differentiable. The function g has to be differentiable at any x, and then function f has to be differentiable at the g of x, which is uh, the base of the composition function, right? Then now we can say that the composition functions, the f of x, that is f composed g of x, is differentiable at x, and then f prime here, that's the key part that you have to look at it, right? How do we take the derivative of this composition function? First, you take the derivative of the outside functions, right, with the inputs of the inside functions, times with derivative of the inside functions. So what you need to be careful is, a lot of times the student would be careful is like the common mistake that I see is this: we would take the derivative of the outside function, but forget to put the entire inside functions back into that. So that's something that you need to be careful with it, right? And there is a different notation that we can use also, which is Leibniz notations. That's basically like rewriting in terms of substitution format. So as you can see that the inner function g of x, we can denote it as a variable u. So therefore, the functions, like the composition function, will become what? F of u, right? So that will be represented by another variable y. So when we are taking derivatives of this composition function, that will become what? Dy dx. That's the Leibniz. So when I take the derivative of that, first we are taking derivative of outer function first, right? Outer function first, which is the y. So we will be taking derivative of y, but the independent variable now is the variable that we substituted, which is u. So therefore, that will be dy du, right? Derivative of y respect to u first. And then after that, we need to multiply with derivative of inner functions, which is the inner function u is respect, the independent variable is x. So therefore, this will be du dx. Okay. So this notations, you can use it, but you have to define all the variable again. So I will try to say that, use this notation first, right? And then practice. And you will see that the Leibniz notation more and more later on in chapter Calc 2 and Calc 3. So first, what we want to do is we want to a little bit review on composition functions, right? It is very important that we will be able to decompose it very quickly, and then being able to see what will be the most outer functions, the next inner functions, and then the next inner functions, so on and so forth. Because remember, using the chain rule, we need to take derivative of the most outer function first. So if given to you the uppercase f functions, and that function is defined as f compose g of x, which is a composition functions. And then now we want to decompose it and then find out what is my f functions and g functions going to be. I would say that pause for a second and then, try to work on this and then see which one you think is f functions and then which one you think will g functions going to be. And then let's check with this answer, right? Okay. So in this case, I can see that the outer functions, the f functions, will be x to the second power, the power, and the inner function will be x plus 1. For part B, my outer function will be the square root functions, which is square root of x, and then the inner function will be x squared plus 1. And the part C, again, the outer function will be 100 power, x to the 100 power, and then g of x will be x to the third minus 1. For D, my outer function will be 4 cosine x, and then my inner function will be x to the third power. So that when we do the composition function, it will give you f. And compose it in an order of that, it's defined this way, right? So the next one, part E, my outer function will be the tangent functions, and the inner function will be 4x to the third plus x. And lastly, my outer function will be x to the 9 power, and the inner function will be x minus 2 over 2x plus 1. There are more, messier problems that we have, but, because we know that some of the functions can be composed of 3 functions or 4 functions, right? We're going to look at it as we move on to our example. So now let's take a look at taking derivative of these functions. So we want to take the first derivative of the given functions right here. Okay. So part A is basically the problem that we did in 2.3, and now we're going to be using the chain rule to work on this. So when I'm doing these problems, like, if you are not used to with this, I will recommend, you try to write it this format so that you can see which order of, derivative we need to take, right? So remember that the very first function in this case is the most outer function, which is the power functions. And the next one will be what? The inner function is x plus 1. So when I take the derivatives, I will take derivative of the outer functions, the power function first, and then the times with derivative of the inner functions, right? So this is like, the order that I will try to write it down and see myself until I feel comfortable and thinking about it mentally. So when I take derivatives respect to x of the functions, right, then this will become derivatives, right? We will be taking derivative of the outer functions. X plus 1 square. So this will give us the y prime, right, equal to, that will be, taking derivative of the power function. So how do we take the derivative of power functions? Bring down the power, and then what? Minus 1 to the power. So 2 minus 1. That's the power function. And remember, I mentioned it earlier, the inside part, right, will be stay as what? The inner functions, which is going to be x plus 1. And at times with derivative of the inside functions. So I'm writing down step by step for a few problems so that we will be able to see how the process works. And then after that, we want to just write it down right away. So this will be 2 times x plus 1 times with derivative of the inside functions. Derivative of x is 1, derivative of 1 is 0. So therefore, I will get 2x plus 1. Right? Notice that if you only think about the power function, you might be thinking that only the power functions is same thing as taking derivative of the power function, then it will be wrong because, oh, you will totally like, mess up on the part of taking derivative of inside functions, right? In this case, it's like, coincidentally, or the problem is formatted to become what? Just x plus 1. So the derivative of that is only 1. Okay. Now, let's continue on the next example, part B. Y is equal to, so very similar, right? But this time the inner functions, the polynomial is like 3 terms. So when I look at this, I will see that the outer function will be 12 power, and the inner function will be x to the third plus 7x plus 1. So now, taking derivatives respect to x on both sides, right? So x to the third plus 7x plus 1 to the 12 power. So what we do is we take the derivative of the outer function, which we already know, that will be the power functions. So when we take the derivative of the power functions, and you bring down the number 12, right? And then minus 1 to the power. And remember the inside of that power function will be what? The inner functions, which is x to the third plus 7x plus 1. And then times with derivative of the inner functions. I will recommend you write it down this step by step all the time until you feel very comfortable, right? If you are barely practicing it, I would just recommend that, uh, do write this step down. So 12, that will become x to the third plus 7x plus 1 to the 11 power times we're now taking derivative of inside, which is going to be what? 3x squared plus 7 plus 0. Right? So this part I will not write it down because we have practiced it enough already, right? From the back. So now you can see that this, you can leave your answer in product format, right? But simplifying a little bit will be what? 12x to the third plus 7x plus 1 to the 11 power times with 3x squared plus 7. And that will be my final answer. I will leave it as it is. Right? Now let's take a look at on the example number part C. Right? So for part C, the outer function is the radical functions, right? And then the inner function is x squared plus 1. So for the radical functions, we will look at it as what? 1/2 power. So when I take the derivative, before I take the derivatives, I can always rewrite this, which is going to be what? X squared plus 1 to the 1/2 power. So taking derivatives respect to x on both sides, right? Always consider you are taking derivative respect to which variable, because you may need to learn go all the way up to calculus 3, and which is going to be multivariable. So it's important to know you're taking derivative with respect to what. So this will become y prime is equal to, now taking derivative respect to x on the right hand side, the power. First, we already know that the outer function is 1/2 power. So bring down the power, right? Times with 1 minus to the power. And remember the inside will be the same as the inner function, which is going to be x squared plus 1. And then times with derivative respect to x of the inner functions, which is x squared plus 1. So this will give us y prime is equal to 1/2 x squared plus 1 to the negative 1/2 power times with derivative of inner function, which is going to be 2x plus 0. So simplifying a bit, right? this 2 and then this 2 will be canceled to reduce it. So I'll have x times x squared plus 1 to the negative 1/2 power. Or if you want, you can write it into the positive exponent by reciprocating it. But for me, it is okay. Okay? Because at this level, I assume that we all know how to simplify it. Example D. So for this problem, I can see that the most outer function will be my square root functions, and the inner function will be 4x minus square root of x, right? Binomial right there. So I will rewrite it as like, a power functions on each of them to make it easier for myself. So that means it will be 4x minus x to the 1/2 power, quantity to the 1/2 power. So when I take the derivatives respect to x of the functions, and I will be taking derivatives of the outer power function, which is this 1/2. So my y prime will be equal to bring down the power, which is this one, 1/2, and then what? Minus 1 to the power. And remember the inside of when we take the derivatives, right, of outer functions, the inside will be what? Still the inner function, which is 4x minus x to the 1/2 power. Then times with taking derivative respect to x of the inner functions on the next step. So this will give us 1/2 times with 4x minus x to the 1/2 power to the negative 1/2 times with now taking derivative of this, the inner functions, derivative of the first term will be 4. Taking derivative of the second term, which is going to be 1/2, bring down the power and minus 1. So 1/2 minus 1 will be negative 1/2. So this will be my final answer, unless you want to, you can change everything into positive exponents. Or you want to simplify further if we need to take the second derivative and so on and so forth. Right? So, it's not a bad idea to practice simplifying. When we need it, you will be able to simplify a lot faster. Let's take a look at so E is y equal to tangent square x. So a lot of times, like, we tend to make mistake on this, right? By taking tangent as an outside function. Remember, tangent square x, that is basically talking about tangents x quantity square. So, the outer functions in this case is what? The power functions, and the inner function is tangent x. So now, seeing this clearly, we will take derivative respect to x of this composition function. So derivative x, and then taking what? Tangent square x. To write it easier, I will just write it like this, right? So now, when we take the power functions, that will become what? Bring down the power, and then tangent, right? X, and then this is 1 minus power, so 2 minus 1 will become just 1. Times with, right? Let me write it down. 2 minus 1, just for your notes purpose. And then times with derivative respect to what? Inside function, which is the inside function is tangent function. And notice that by writing this way, see my inner function is tangent right there. Right? So a lot of times, like, we tend to make mistakes on writing on this part. You have to be extra careful because writing this way is very clear, right? You can, like I showed you earlier, you can write it down the power, bringing down the power minus the power. The insides will be the same. But writing like, a more neater formats what we learn in trigonometry functions, you may get wrong, right? If you are not paying attention to it. So just be careful. So now this will become what? 2 times tangent x times the derivative of tangent is secant square x. And that will be my final answer. Let's take a look at on F. So in this case, the outer functions is 4 times cosine, right? That's outer functions. And then the inner functions is x to the third power. And since 4 is a constant, I can just take the derivative of what? Cosine function, right? Using the formulas, take derivative formula from 2.3. So when I take derivatives on both sides respect to x, then that will be y prime is equal to derivative of constant times the function is what? Constant times derivative of the function. So derivative of cosine, that will be what? Negative sine, right? And then what? The inside will be still the same, right? Negative sine, and then the inside will be still the same. And what is inside? X to the third power. And times with derivative of the inner functions. Don't forget that. So x to the third. So now I will get 4 times negative 4 times sine of x to the third times the derivative of inner function will be what? 3x squared. So when I simplify, that will be negative 12x squared sine of x to the third power. And that will be my final answer. Let's take a look at on the next example, G. So when I take the derivative respect to x on both sides, and this is gonna look like derivative of tangent of 4x to the third plus x. And notice that in this case, the outer function is tangent functions, and the inner function is 4x to the third plus x. So when using the chain rule, taking derivative of the outer functions, derivative of tangents will be what? Secant square x, which is in this case will be, we need to put down the inner functions, right? Usually that's why, usually the mistake is writing too fast, secant square x. Actually what? We need to write down the whole entire inner function, which is going to be 4x to the third plus x times with derivative respect to x of the inner function, which is 4x to the third plus x. So finally, I got my final answer by taking derivative of inside, which is times with 12x squared, right? Bringing down 3, 4 times 3 is 12. Subtract 1 to the power, which is going to be 2. And then derivative of x is 1. And this will be my final answer. Let's take a look at on H. So for example H, when we take the derivatives, first we need to take derivative of each term. And when we take the derivative of each term, that's where I need to use the chain rule, right? So derivative respect to x of both sides, that will become derivative respect to x of the first term. I'm going to skip one step, right? So that we can move it a little bit faster. And then plus derivative of derivative respect to x of the second term. And this is where we need to use the chain rule. For the first term, we can see that the outer function will be x to the third power functions. And then the next functions, right? The next functions will be secant functions. And then the last function is what? 4x. See, this is the 3 functions there. So when we take the derivative of that, that will become y prime is equal to derivative of the power functions, which will be bringing down the power 3, right? And then 2 minus 1, or 3 minus 1, right? Subtracting the power. And remember the inside, it has to be whatever inside is, which is secant of 4x. Then times with derivative of the next inner function, which is secant 4x. See, once you have the compositions of three functions together, writing down the step-by-step is getting longer and longer, such that you want to practice it on writing and then see clearly on those compositions with two functions and then stop writing every single step. Okay, once we get more complicated, because that will, reduce the time, but for this problem, I will write it down as, as an example, and it's longer to write it down also. Now, let's take a derivative of the second part, which is the same format, but except what we have cosecant right there. So this will become, when we take the derivatives of the second portion, that'll be 3, and then minus 1 on the power, 3 minus 1. Okay. And the inner function will be cosecant of 4x, and times taking derivative respect to x of the inner function, which is cosecant 4x. Has the same format except what this become cosecant. So now we can continue and then simplify a little bit and then take derivative also. So that will be 3 secant square 4x, right? 1 power less, times the derivative of this, right? Secant 4x. So we need to take derivative of what? Secant first in this case. Right? So the derivative of secant will be what? Secant. Let me write this down with a different color. The derivative of secant is secant times what? Tangent. And remember, the inner function will be the same as the inner function, because a lot of time right here, the mistake is writing down secant x, tangent x. That's the mistake. Okay. So we need to remember secant of what? We have one more inner functions. Secant 4x, tangent 4x, times with derivative respect to x of the most inner function now, which is 4x. And then plus, same thing for the next one, 3 times cosecant to the second power 4x times what's now derivative of cosecant, right? That is derivative of cosecant, that is negative cosecant cotangent, right? Negative cosecant cotangent. So now remember, the inner functions of cosecant and a cotangent is what? The most inner function, which is 4x, and times with derivative of the most inner functions, which is 4x. So finally, now we can write it down. 3 times secant 4x times secant 4x tangent 4x times the derivative of that. 4x will be just 4, plus 3 times cosecant square 4x negative cosecant 4x cotangent 4x, and then times what's 4. Finally, simplifying this part, 4 times 3 is 12. Secant secant square 4x times secant will be 3 secant cube 4x tangent 4x. Now we minus 12 times cosecant cube to the 4x cotangent 4x, and that will be my final answer. Okay. So, notice that writing this step by step take a while. Okay. So that's why you want to practice it when you are doing homework with a few of them. And then after that, we will be skipping, right, all the way down to this step and then this step. So 2 steps, and then I will get my final answer. But in order to do that, you need to clearly see which functions we need to take derivative first, second, third, and then take it correctly. Okay. So let's take a look at our next example. So this time you should see that the composition functions is the most outer is sine, and the next inner is cosine, and the last one, right, the most inner one is tangent x. So we're gonna take derivative in that order. So when I take derivative respect to x of y, and that's taking derivatives respect to x of this composition function, sine, cosine, tangent of x. So taking derivative of the most outer functions, which is derivative of sine is cosine, and then inner functions, times with, right, derivative of the next inner functions. So remember, the inner functions of sine is what? Cosine tangent x. That is the part that you need to write it correctly. And then the next inner function will be cosine, which is cosine tangent x. So taking derivative of that will be cosine of tangent x times with, now derivative of cosine is negative sine of the inner functions. And that inner function is basically what? Tangent x. Then times with derivative respect to x of the most inner one, which is tangent x. So finally, cosine of tangent x times with negative sine of tangent x times the derivative of tangent is secant squared x. And this will be my final answer, unless you want to rewrite it then. That's perfectly fine. So next problem, starting from next problem, I'm gonna just write it down, the taking derivative part one by one. Okay. And skipping those like, step by step part. G. Let's take a look at on that part. So this is a more complicated one. First, we need to take a look at on, break it down correctly, right? Composition functions. So you might want to, pause it and break it down and then see you got the same answer as me or not. So the function is y equal to sine to the fourth power cosine to the third power of x squared. So the most outer functions in this case will be x to the fourth power function, the power, full power function, and then the next one will be sine function. And the next one will be not the cosine to the third power functions, and then cosine. And then lastly will be x to the second power. So this is the order that we need to go. So take a look at on this. When we take derivatives respect to x of both sides, I'm going to take the power functions. So that means bring it down 4. And then inside of the power function is still the same function, which is everything below of that. That's how you can see it. So that means the inside part, right? The inside part is sine of what? Cosine to the third power x squared. And the power functions, when we take the derivative of that, that will be what? Bring down the power and minus 1, so it will be what? Sine to the third power now. Times with the next derivative that we need to take is sine. So derivative of sine is cosine functions. And inside of its cosine is everything the same, right? Meaning what? Everything below of that will be still the same. So that's basically talking about what? Cosine to the third power of x squared. Follow? And then times with the next, we're going to be taking derivative of the power. So that it will be bring it down 3. Okay. And then everything inside of that power function is the same, which is what? Cosine and then below. So cosine of x squared. But when we take the power functions, we bring down the power and we need to subtract 1 to the power. So it will become cosine squared now. And then times with everything. And the next function will be cosine functions, which is derivative of cosine is negative sine. And then inside function will be the same, which is x squared. And then times with the derivative of the most inner function, which is 2x. And that's how long it is for taking derivative of each part. So this part, right? This is the derivative of the power function's full power. And then the next will be what? Derivative of the sine. And that is the derivative of the sine part. Right? Everything inside of the sine is like the inner functions. The power, cosine, and stuff. And then next thing that we look at is what? The power functions. So here, bring down the power and minus 1 to the power. And then the next one will be what? The cosine functions. So derivative of cosine functions. Uh-oh, this is bad. So derivative of cosine functions right here is right there. And then lastly will be x squared. So it could be done in one step, but you really need to be careful because it takes it could make a lot of mistakes, right? And then finally, if you want to simplify, you can simplify, which is 4 times 3 times 2x and negative, right? So that will give me negative 12x. Oh no, 24x. Negative 24x, and then sine x squared cosine square x squared, and then cosine to the third power, right? X squared, and then lastly will be sine to the third power cosine to the third power x squared. So you can rewrite it as your final answer. So let's take a look at our next example. So for this problem, I will first rewrite it to negative power so that I don't need to use the quotient rule, right? So this will become 2x to the fourth minus x squared plus 8 to the negative 1 power. So from here, I can see that negative 1 power is the most out of functions, and then after that will be just a polynomial, 2x to the fourth minus x squared plus 8. So that makes it a little bit easier. So when we take the derivatives respect to x, that will be y prime, and bring down the exponents, right? I'm taking derivative of the most out of function. So bring down the exponents, and then what? Minus 1 to the exponent. Negative 1 minus 1. And the inner function is the same. So it will be 2x to the fourth power minus x squared plus 8, right? Everything. And then times with now derivative of the inside function, which is the last functions right here. That will be 8x to the third power, because bring down 4 and then times with 2, and minus 1 to the exponent, minus 2x plus 0. So finally, this gives us negative 2x to the fourth power minus x to the second plus 8 to the negative 2 power. and then 8x to the third minus 2x. If you use, if you use the quotient rule, right, since the beginning, if you use the quotient rule and take the derivative and simplify it, we should be getting the same answer. Right? That's something that we need to clear about. So let's take a look at our next example. So this problems will be similar to the previous one. So we're going to rewrite it. That will become x to the second plus x plus 1, and then to the negative 1/3 power. So you can see that the outer function is negative 1/3, inner function is what? X squared plus x. So my y prime will become, bring down the exponent, negative 1/3, and then subtract 1 to the exponent, which is negative 1/3 minus 1. And then the inner function is the same, so x squared plus x plus 1, and times with derivative of inside function, which is will be 2x plus 1 plus 0. Simplifying further, it will be negative 1/3 x squared plus x plus 1 to the negative 4/3, and then times with 2x plus 1. And that will be my final answer. And let's take a look at on the last example, M. So for this problem, we have the power functions, and then inside is rational. So this, we need to use the chain rule plus the quotient rule. So let's take a look at on this. When I take the derivative respect to x for the chain rule, first we take the power, so bring down the 9, right? And then what? Minus 1 to the power. And the inside part is stays the same, which is going to be x minus 2 over 2x plus 1. Times what's now derivative of the inside functions, which is this portion, right? That we need to do. And when we take the derivative of that, will be the quotient rule. So I take the derivative of the numerator first. So when I take the derivative of the numerator, that will be 1 minus 0 times with the denominator, which is 2x plus 1, minus, right, minus numerator, which is x minus 2, times with derivative of denominator, which will become what? 2 plus 0. And all over the denominator square, which is 2x plus 1 quantity square. So if we simplify a little bit, see, notice that if you are clear and if you got used to it, you can be done like mine, right? The way that I'm doing. I don't need to write it down every little detail on it. I read it out loud on the formula and then take derivative right away. Right? And that requires lots of practice. So finally, my final answer is 9 times 2x plus 1 to the 8th power, and then times what's, and right here you can simplify a little bit if you wanted to. That would be what? 2x plus 1, and then minus 2x plus 4 when I distribute it, and then it will be what? 2x plus 1 quantity square. So finally, this will become 2x, and then minus 2x will be gone. 1 plus 4 is 5, and 5 times 9 is what? 45 over what? 2x plus 1 quantity square times with the next fractions, which is x minus 2 over 2x plus 1 to the 8th power. And you can simplify further by breaking down this rational into 2x, 2 minus x to the 8th power, and then 2x plus 1 to the 8th power, so that in the denominator you can combine the exponent together. Okay, so this all 45 x minus 2 to the 8th power over 2x plus 1 to the 10th power. And you may write it down either way, and then that's mainly for continuation purpose later on if we need to take the second derivative or not, right? And this is the end of this sections, and then mainly this section is practicing on this I would say mechanical part, because taking derivatives, right? Not much of theoretical, is a mechanical part that you need to get used to it. That's how to take the chain rule, right? Use the chain rule to take the derivatives, and then practice a lot. Okay. Not this.